Hello and welcome to Python for Everybody. We're doing some sample code. You can get a hold of the sample code zip if you want to follow along. And so we're picking up in the middle here where we are running a simple spider that's retrieving data and putting it into running this spider.py file, and it's cruising around and doing things. And the beauty of any of these spider processes is I can stop anytime and just hit Control C. And so we take a look at the spider.sqlite file and retrieve it, and it looks like we got 302 pages. I don't know how many we got retrieved. 70. Okay, there we go. We got about 100. Oh wait, I'm looking for the wrong thing. No. Yeah, we got about 107 pages. So what we're going to do now with 107 pages is we are going to run the PageRank algorithm. Okay, so let's take a look at that code. So the idea of PageRank, we're going to run this PageRank algorithm. The SP reset just resets the PageRank, and SP rank runs as many iterations of PageRank. So the basic idea is that if you were to look at the links here, you know, we think of page 1 pointing to page 2 gives some of page 1's love to page 2. Page 4 has some value that it gives to page 1. You go on, and page 2 gives love to page 46, over and over and over again. And so, but the problem is that how good is page 1, and how much positive karma does it give to page 2? And so what happens is we start by giving every page a rank of 1. We say, look, everybody starts out equal. But then what we do is we divide up in one iteration of the PageRank algorithm. We divide up the goodness of a page across its outbound links, and then accumulate that, and that becomes the next rank. Okay, and so let's take a look at the code for the PageRank algorithm. So this is pretty simple. It only imports SQLite 3 because it's really doing everything in the database, right? It's going to be updating these columns right here in the database. And so we're going to do some things here to speed this up. This rank runs, if you're thinking of Google, this rank runs slowly, and it's going to run continuously to keep updating these things. So the first thing I do is I read in all of the from IDs from the links. Select distinct throws out any duplicates, and so I have all the from IDs, which are all the pages that have links to other pages, because all the pages are in pages, but in links to have a from ID, you have to also have a to ID. Okay, and so we're also going to look at the pages that receive PageRank, and we're kind of pre-caching this stuff. Okay, and so we're going to do a select distinct of from ID and to ID and loop through that group of things. And we're making a links list here. And so we're saying if the from ID is the same as the to ID, we're not interested. If the from ID is not already in my from IDs that I've got, I'm going to skip it. If the to ID is not in the from ID, meaning that this is a to ID that's not also, we don't want links that point off to nowhere or point to pages that we haven't retrieved yet, and that's what this is saying. So this is really going to give us, it's a filter on the from IDs and the to IDs from the links table, so that it only are the links that point to another page we've already retrieved. And then we're going to keep track of the entire superset of the to IDs, the destination IDs. And I'm just putting these all in lists so that I don't have to hit the database so hard. Okay, so this is getting what's called the strongly connected component, meaning that any of these IDs, there is a path from every ID to every other ID eventually. So that's called the strongly connected component in graph theory. Then what we're going to do is we're going to select new rank from pages where for all the from IDs, right? And so we're going to have a dictionary that's based on the ID, the primary key, that's what node is, equals the rank. And so if we look at our database, that means that for the part of the strongly connected component in links, we're going to grab this number and stick it into a dictionary based on the primary key of this, this number right here. So we're going to have a dictionary that's this mapped to that. Again, we want to do this as fast as possible. Now we're only doing one iteration at the beginning, so it asks how many times you want to run it. Okay, so we just make an integer of that. We check to see if there's any values in there. If there are no values, we are bad. And now we're going to go I equals 1 to range many. This is going to be 1 to 1, so it might run however many times. And then what it's going to do is it's going to compute the new page ranks, and so what it's really going to do is it's going to take the page rank, the previous ranks, and loop through them, and this is the previous ranks is the mapping of primary key to old page rank. Okay, and for each node, we're going to have total equals total plus old rank, and then we're going to set the next ranks to be 0. Okay. And then what we're going to do is figure out the number of outbound links for each page rank item. So node and old rank in the list of the previous ranks. These are the IDs we're going to give it to. And so for this particular node, we're going to have the outbound links, and we're going to go through the links and not link to itself, although we made sure that doesn't happen. We make sure that this. But then we're going to make a list called give IDs, which are the IDs that node is going to share its goodness. And now what we're going to do is we're going to say how much goodness are we going to flow outbound based on our previous rank of this particular node and the number of outbound links we have. So that's how many that's how much we're going to give in our outbound links. And then what we're doing is all the IDs we're giving it to, we started with the next ranks being 0 for these folks. These are the receiving end, and we're going to add the amount of page rank to each one. So whatever this is, so we'll go through all of the links, give out fractional bits of our current goodness, and it's accumulated in each one. And so eventually, all the incoming links will have granted each new link value. Okay. Now I'm just going to run through and calculate the new total, and this is this evaporation. The idea is that you can't. It has to do with the PageRank algorithm that there are dysfunctional shapes in which PageRank can be trapped, and this evaporation is taking a fraction away from everyone and giving it back to everybody else. And so we add this evaporative factor. And then we're going to do some computations just to show some stuff, and that is we're calculating the difference, the average difference between the page ranks. And you'll see this when I start running it. And that is telling us, this is going to tell us the stability of the page rank. So from one iteration to the next, the more it changes, the least stable it is. And you'll see in a sec that these things stabilize. And then we'd say, what's the average difference in the page ranks per node, which is what this is. And that's what we're going to print. And now we're going to take the new ranks and make them the old ranks, and then run the loop again. So I'm not actually updating the database each time through the PageRank iteration, but then at the very end, I am going to do the update for all of these things and update all of the rankings with a new rank. So I'm doing an in-memory calculation so that this loop here runs screamingly fast. Even if I want to do like this loop 100 times or 1,000 times, it's really all just in-memory data structures. Okay, so it's probably easier just for me to show you this. It'll be very, the code runs quite simply. Python 3 sprank rank.py. And so I'm only going to run it for one iteration, and that means that this loop here is just going to run one time. And so it's going to start with the page ranks the new rank of 1, and it's going to just run one iteration and put the rank there, okay? And then update this as well. So let's go ahead and run that once for one iteration. Okay, and so it ran one iteration, and the average change between the previous rank and the new rank is 1. So there, it's actually quite crazy. So I'm going to refresh here, and you'll see that the old rank was 1, and the new rank went way down, way down, way down, way down, down a little bit, down, down some, up a whole bunch, down, down, up. So you see that they went down and up. Now the sum of all of these numbers is going to be the same, right? Because all it did, it was like floated out and recalculated it. And so that's what happens with PageRank. And so what will happen is if I run one more PageRank iteration, these numbers will be used to compute the new rank, and then these will be calculated to the old rank. And so you'll see that these will they will change again. So I'll just run it one more time. So I'm going to run one iteration, and then I'm going to hit refresh. So you see all these numbers got copied over, but now there's a new rank that's computed based on these guys. And so they're getting, this one went up. This was 0.13. That's gone up a little bit. This one's gone up some more. This one's gone up. This one went down, right? So this one went down from 6 to 8. And you can see that the difference is now the average difference between this number and this number across all of them went from 1 point something to 0.41. And you'll see that with these very few pages, this PageRank converges really quickly, okay? So let's run it again. And I'll just run 10, and you will watch how this converges. Okay, so there you go, it converges. So, and you're seeing now after like 12 iterations that the difference between the old rank and the new rank, well, that's because it's that old rank. I'll run one more iteration so that you can see. So this old rank is less than, 0.005, so now you can see that these numbers are sort of stabilizing. This is the average, that 005 number is the average difference between these two things. Now, if we're going to pretend to be Google for a moment, we can say Python 3 spider.py. So let's just do 10 more pages. Now what's going to happen here is these new pages are going to have page ranks of 1. Okay? So let's get out. So if I do a refresh now and I look at new rank, so there's these guys that have high rank. What you'll see, I hope, yeah, okay. So you see new pages, right? These are the new ones that we just retrieved. I don't know if they're linked or not, and they all got 1. So some old pages are way up, 14. Some pages, if we go downwards, are way down, right? So these are like useless pages. They point to somewhere, but nobody points to them. That's what happens with these page ranks, okay? So what happens is the new records get this 0.1, and so if I run the ranking code again, and I run, let's just run 5 iterations, you'll see that the average delta goes up just briefly as it sort of assimilates these new pages, and then it goes right back down again. And so that's what's happening with Google. It's sort of running the spider to get more pages, then running the page rank, which gets disturbed a little bit, but then it reconverges very rapidly. And of course, they've got billions of pages, and we've got hundreds of pages, but you get the idea. Okay, and so I can run page rank like 100 times, and after a while, it just sort of hardly is changing. So that's 2.7 to the negative 10th power. So now, let me run it one more time to update the stuff. And if I refresh this, you're going to see, look at how stable these numbers are. 14, 9, 4, 3, 5, 9, 1, 5, 6, 7. The difference is there in the 7th one. So that's why this whole page rank is really cool. It seems like it's really chaotic when it first starts out, and away you go. Okay? So that was just this, SP rank, right? SP rank. And SP reset, we can look at that code. I won't bother running it. It just sets the old rank to 1. That's it. That's as much code as you got. It just restarts it and lets it rerun. So I'm going to stop now, and I'm going to start a new video where I talk about this phase here where we're actually going to visualize the PageRanked data.